We will examine an example of forced convection, where convection basically transports material in the streamwise direction, and there is cross stream diffusion, and because of convection the rate of diffusion is significantly enhanced. In this particular example of dispersion, in a packed column. Okay. So, if you recall, we had discussed the packed column earlier. It consists of a column densely packed with particles. These particles could be of any shape, through which the fluid is forced through with a superficial velocity Vs, and the diameter of the particle, or the equivalent diameter, was dE. Okay. And the velocity of the fluid through the pores is the characteristic velocity of the fluid through the pores is the ratio of the superficial velocity. Recall, superficial velocity is the velocity through the cross section when there are no particles present. When there are particles present, the pores constitute only a part of the total cross sectional area. The ratio of the area of the pores in the cross section to the total area is the porosity epsilon. And since the cross sectional area available is epsilon times the area of the column, the velocity of the fluid through the pores is the superficial velocity divided by the porosity. And I had just stated for you at that point that just based upon dimensional analysis, the diffusion coefficient is equal to Vs by epsilon, which is the velocity scale, times the equivalent diameter of the particles. Okay. And this just followed from dimensional analysis. Here I will go through a simple example of a structured porous material in order to demonstrate how this scaling comes about. Okay. So, I will consider a structured porous material in 2 dimensions made of rectangular elements. Okay. In which each row is staggered by 1/2 of the total width. Okay. One half of the repeat length. Okay. Okay. Though I have not drawn it to scale here, in this particular case the distance between the obstructions, which are rectangular in this case, is actually much smaller than the size of an obstruction. Okay. And I will consider the repeat length here as L. Okay. So, this repeat length is L. Okay. And I will use a coordinate system. So, let me put the repeat length above. And I will use a coordinate system where this is the flow direction and this is the cross stream direction Z. the flow direction I will call as x. Okay. So as not to confuse, I will take the scale down. Okay. So this is the direction z, which is the cross stream direction. Okay. So this is z is equal to L, this is z is equal to 2L, this is z is equal to minus L, and this is z is equal to minus 2L. Okay. Okay. And a fluid is introduced here at the center, a solute is introduced here at the center, okay, and it flows through and it spreads as it goes around, okay, in tortuous paths around. Okay. Okay. So, you are introducing a solute exactly at the center, and you would like to see how much it spreads as it goes through this array of obstacles. Okay. So, that is the idea. Okay. So, this is a simple structured porous material, and we will use simple rules here. Okay. So, you can see that at each T junction, okay, the fluid that is coming here, okay, is going to bifurcate. Okay. And we will assume that two equal volumes go in the two horizontal directions at each T junction. Okay. That equal volumes, okay, one half of the incident fluid goes to the right and the other half goes to the left at each T junction, okay, in the streamwise direction. Okay. And then at the perpendicular junction, okay, you have, okay, two streams that are merging together. Okay. You have two streams that are merging together at each perpendicular junction. Okay. Okay. So, at each perpendicular junction, I will have two streams that are merging together. Okay. So, I will have two streams that are merging together at this junction, okay, and then it goes upwards. The assumption here is that the concentration, okay, the concentration C here, okay, is equal to 1/2 of the concentration on the left plus the concentration on the right, okay, is equal to 1/2 of the concentration on the left plus the concentration on the right. Okay. So, those are simple rules. Okay. So, let us assume that the concentration here is just equal to 1. Okay. Concentration here is equal to 1. Okay. So, C is equal to 1 here, and C is equal to 0 in the fluid everywhere else. Okay. And then you can ask what happens to the concentration at each, as each stream splits and rejoins around an obstacle. Okay. What happens to the concentration as each stream splits and rejoins at each junction. Okay. So, after the first time that it splits and rejoins, okay, so okay, you can easily see that the concentration is 1 here. Okay. So, I will write the concentrations in blue for you. Okay. The concentration is just 1 over here, okay, at the inlet, okay, where the solute is incident. Okay. I scale it by the concentration of the solute at the inlet. Okay. So, the scaled concentration is just 1 here. Okay. At this point, these two streams, okay, with concentration 1 and concentration 0 join and go upwards, and when it goes upwards, the concentration obviously has to be equal to half here and half here. Okay. It has to obviously be equal to half and half, okay, because it is the average of the two concentrations that are incident. Now these join once again. Okay. So, now these join once again, and over here you can see that half and 0 average. Okay. So, the average is 0 here, the average is 0 here and half. So, here you will have 1 by 4. The average here will be average of half and half, which is just 2 by 4, and over here it will be 1 by 4. Okay. And you can plot the, you can calculate the next one. Okay. The concentration is 0 everywhere else, and so you will get here 1 by 8, 3 by 8, 3 by 8, 1 by 8. Okay. So, the concentration progresses in this manner. Okay. So, the concentration progresses in this manner. You have 1, half, half, then 2 by 4, okay, 1 by 4, 1 by 4, and then 1 by 8, 3 by 8, 3 by 8, 1 by 8. Okay. So, each concentration is the average of the two adjacent concentrations below. Okay. Each concentration is the average of the two adjacent concentrations below. Okay. Okay. Similarly, for this one, okay, it is the average of the adjacent concentrations. In this case, the adjacent concentration on the right is 0, okay, and so on. Okay. So, this has a specific form. Okay. So, numerator in this is, if you write it out, it will be 1, okay, 1, 1, 1, 2, 1, okay, and so on. Okay. And the denominator, so if this is, let us say this is for n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3. Okay. So, this is the numerator. Okay. And the denominator is equal to 2 power n. Okay. Is equal to 2 power n. Okay. So, this is the sequence of concentrations that you get as this is, as the solute passes through around these obstacles in a porous medium, in this structured porous medium. Okay. This thing is called the Pascal triangle. Okay. Okay. And this can also be written as NCM, okay, where n is the row index. Okay. So, for the first index n will be 0, m will have to be 0. For the second one, n is equal to 1 and m is equal to 0 minus 1 0 1 sorry 0 1, and the second one m is equal to 1 and n is equal to 0 1 2, etc. Okay. The combinatorial factor. Okay. So, this is the combinatorial factor. Okay. So, this is the way the concentration spreads as the material goes through the structured porous medium, okay, in the streamwise direction. So, if this repeat length is L, then this I can write it as, okay, x equals 0, okay, x is equal to L, x equals 2L, x equal 3L. Okay. So, this is the way the concentration spreads. Okay. Now, I can calculate the standard deviation of the concentration. Okay. The standard deviation or the mean square displacement in the z direction. Okay. This is the variance of the distribution or the mean square displacement in the z direction. Okay. This is going to be a function of x. Okay. This will be equal to the summation of Ci times Zi square, okay, divided by summation of Ci, okay, where the I index is going over all of these different locations. Okay. Okay. The concentration is 0, of course, if Z becomes large, and therefore, the summation is finite. So, I just sum out sum Ci times Zi square over the sum of Ci. In this particular case, the concentration is normalized. So, the sum of Ci, as you can see in each of these cases, is equal to 1. That is because I have used a normalized concentration. Okay. And Zi is, for example, for these two cases, okay, for these two, okay, for these two, for example, Zi is L by 2. Okay. For these two, Zi is equal to L by 2, okay, because L is the repeat spacing, and this each successive row of these obstacles has been displaced by half the length. So, Zi is equal to L by 2 in this case. Okay. So, in this case, for the first row I can write it as, okay, is equal to L by 2 the whole square into 1 by 2 plus minus L by 2 the whole square into 1 by 2. Okay. Okay. And this turns out to be equal to L square by 4. Okay. That is the mean square displacement in the z direction. Okay. That is the mean square displacement in the z direction at x is equal to L. Okay. You can calculate it for the second row. Okay. For the second row, okay, for these two, okay, for these two, z is equal to plus or minus L, and for the center z is equal to 0. Okay. So, I will get okay, which is equal to L square into 1 by 4 plus L square into 1 by 4. Okay. And this you can easily verify is equal to L square by 2, okay, at x is equal to 2L. Okay. And you can calculate it for other rows as well by repeating these procedures for generating the concentrations. And for each higher row you will find that the formula that is satisfied is that the mean square displacement in the z direction is equal to, okay, x L by 4. Okay. Okay. At x is equal to L, it is L square by 4. At x is equal to 2L, it is L square by 2. The next one will be 3L, x is equal to 3L, and you should get 3L square by 4 and so on, okay, if you do the calculation. Okay. So, therefore, the mean square displacement is x into L by 4. Okay. Now, I can express this in terms of the superficial velocity, because the distance x travelled, okay, the distance travelled x, okay, is going to be, okay, streamwise distance if I were to express it in terms of the time of travel, if I were to express the streamwise distance in terms of the time of travel, that streamwise distance will be equal to, okay, t into Vs by epsilon, okay, which is x. Okay. That streamwise distance is equal to the velocity times time. So, it is equal to Vs by epsilon, which is the velocity through the porous medium times t, okay, that is equal to x. Okay. So, substituting for that into this expression, I get this mean square displacement is equal to Vs T L by 4 epsilon. Okay. Okay, if it is expressed in terms of the total time taken. Okay. Recall that when we had done the problem of diffusion into an diffusion of a pulse, okay, I had said that the mean square displacement, okay, this is equal to 2 times the diffusion coefficient, effective diffusion coefficient times t. Okay, this is in one dimension. For the diffusion of a pulse, the diffusion coefficient, okay, is equal to the mean square displacement, or the variance of the distribution function is equal to 2 d effective into t. Okay. And this gives us, okay, the expression for the effective diameter is equal to Vs into L by 8. Okay, that is the effective diffusion coefficient, 8 epsilon, I am sorry. Okay, that is the expression for the diffusion coefficient. I had started off saying that just based upon dimensional analysis, we had said that the diffusion coefficient is proportional to. Okay. This is not quite equal to, this is proportional to. Okay. From dimensional analysis, you only get proportionalities, you do not get exact relationships. It is proportional to Vs into the equivalent diameter by epsilon. Here, for a structured porous medium in which the length scale is L, I have calculated what is the diffusion coefficient, okay, by relating the spread, the variance of the distribution of the solute concentration, the variance of the solute concentration to 2 d effective times T, where d effective is the effective diffusion coefficient. Okay. So, this note is independent of the molecular diffusivity. Okay. This depends only upon the velocity and the length scale, okay, of the repeat unit. Okay. So, this was solved for a very specific case, for a very specific structured porous medium in one dimension. Okay. If you consider a random medium in multiple dimensions, the coefficients will change, but the dispersion coefficient, the effective dispersion coefficient will still be proportional to the superficial velocity times the characteristic repeat unit distance or the characteristic length scale. Okay. And the idea is as follows. Okay. So, what happens is when you have a structured porous medium, okay, let us just take the structured case. Okay. Okay. You have two fluids, okay, which are coming, one is here, okay, and the other is coming with a different concentration over here. Okay. This cross sectional distance in a porous medium is much smaller than the diameter of the particle. Okay. The cross sectional distance in the porous medium is much smaller than the diameter of the particle. Okay. So, if the flow is such that within the time that it takes for the fluid to traverse one repeat unit, there is sufficient cross stream mixing across this pore length scale, okay, across this pore length scale, not across the particle size or the size of the repeat unit or the size of the obstacle. Okay. You have obstacles and then you have spaces between obstacles which are much smaller than the size of the obstacle itself. Okay. So, if the diffusion across the spacing between obstacles happens sufficiently fast that there is complete mixing, by the time the fluid traverses one repeat unit, okay, then you can consider the fluid to be well mixed within that region before it crosses one repeat unit, and therefore, the fluid velocity at the end of the repeat unit is the average of the fluid velocity at the beginning. Okay. So, basically it is not sufficient for diffusion to, it is not necessary for diffusion to take place over the particle diameter scale. It is sufficient for diffusion to take place across the pore size or the distance between obstacles. Okay. And if that distance is small, then diffusion takes place rapidly across that length scale, and because of that you get a dispersion coefficient which is proportional to the distance travelled, that is in this case the repeat unit length times the velocity. Okay. Provided diffusion is fast enough that there is complete mixing over the length scale of the pore or the length scale between the obstacles. Okay. So, if that is the case, then diffusion takes place rapidly and then you get near complete mixing. Because the fluid is well mixed, the dispersion does not depend upon the diffusion coefficient. Okay. If it were not well mixed, then the dispersion will depend upon the diffusion coefficient. Since it is well mixed within the time it takes to traverse one repeat unit, the dispersion coefficient does not depend upon the molecular diffusion coefficient, because by the time it crosses one unit, it is already well mixed, and therefore, the diffusion coefficient does not matter. Okay. So, what is required in this case is that the time for crossing one repeat unit, okay, the time for crossing one repeat unit is the length of the repeat unit by Vs by epsilon. Okay. That is the time for crossing one repeat unit, okay, has to be larger then the diffusion time across this length. Okay. Then the diffusion time across this length. I will call this distance between obstacles as delta. Okay. If I call the distance between obstacles as delta, then this has to be much larger than the time for diffusion across the length delta, which is delta square by the molecular diffusion coefficient. Okay. Okay. Delta square by the molecular diffusion coefficient. Okay. Okay. Or alternatively, okay, delta square by L square has to be much smaller than d by epsilon by VSL. Okay. D epsilon by VSL is a inverse of a Peclet number. So, delta square by L square has to be smaller than the inverse of the Peclet number, okay, based upon the molecular diffusion coefficient and the characteristic velocity. Okay. So, if this is true, okay, then we can the fluid is there is almost complete mixing of the two inlet streams into a porous region by the time it traverses one repeat distance, and therefore, the dispersion coefficient does not depend upon the molecular diffusivity. It depends only upon the velocity of the fluid and the distance, the repeat unit or the equivalent diameter of the particles in a packed column, for example. Okay. So, this is a simple example that illustrates how forced convection can result in enhanced diffusion. Okay. This dispersion coefficient can be much larger than the molecular diffusion coefficient, okay, in many cases. For example, if you have a repeat unit of a millimeter, say, and a velocity of about a millimeter per second, right, the effective diffusion coefficient, dispersion coefficient is 10 power minus 6 or 10 power minus 7, whereas the molecular diffusion coefficient in liquids is of the order of 10 power minus 9 meters square per second for small molecules. Okay. So, this mechanism can significantly enhance mixing and dispersion, both dispersion of mass as well as dispersion of heat. In both cases, the dispersion coefficients will scale as Vs times L by 8 epsilon, okay, or Vs L by epsilon times some constant prefactor. Okay. So, this is the first principles calculation of the dispersion coefficient in a structured porous medium, okay, with the assumption that two fluid streams that mix at a pore are fully mixed at the molecular level before they exit the pore between two obstacles. Okay. So, with that assumption, since it is already well mixed, the diffusion coefficient, the molecular diffusion coefficient is no longer important, and what matters is the velocity through the pores and the repeat unit distance. Okay. So, this is an example to illustrate that. Okay. So, with this I complete the discussion of dispersion in a packed column. In the next lecture, I will discuss Taylor dispersion, which is the axial dispersion in a pipe. I will continue that in the next lecture. I will see you then.